Hello, y'all. Welcome to lesson 55 of my DP chemistry curriculum. Today we're going over structure 2.3.1. We are starting with metallic bonds, which are the electrostatic attractions between a lattice of cations and delocalized electrons. So we're going to explain the electrical conductivity, thermal conductivity, malleability of metals, as well as a couple other properties. And we'll try and relate characteristics of properties of metals to their uses. So with that said, let's get right into the lesson. So metallic bonding is actually very similar to our other bonding. So in ionic, we get these things called crystalline solids, whoops, which is that ordered structure of repeating cations and anions. Repeating lattice of cations and anions. So the positive and negatives of the ionic compound. Now, in a metallic bond, or in metals, so metallic compound, we also create crystalline solids. Crystalline lattice solids. Now, the difference here is that it is cations only. So only the cations, because metals tend to be cations, but also the whole thing is electrically neutral. So we have to kind of figure out how that works out. And the key is we also have delocalized valence electrons. So when we were talking about things like graphite, or honestly, it was mostly just with like graphite and graphene, our allotropes of carbon, we talked about delocalized electrons. We also talk about it a little bit when we're going through things like resonance. Those electrons move between the bonds. But in metallic compounds, we do have delocalized valence electrons. And this is going to be the single most important part of metals. It's kind of what is going to define every single property they have, and we're going to look at it through the lens of those delocalized valence electrons. Much like we introed at the top, when we look at a metallic bond, it's different than our ionic and covalent bonds because it's not between two atoms. This is specifically the attraction between a lattice of cations, which are once again positive ions, and delocalized electrons. So I think I'm going to start saying DE for delocalized electrons. We're going to write it a lot, so let's try and figure out a way to shorten that. If we take an example like sodium metal, sodium is Na, it has one valence electron. And so when we look at sodium, we have our sodium ions, and I'm just going to try and uh, we'll just put a bunch of these here. And we get this nice, neat ordered structure. So we'll try and get a full 6. So here's our ordered lattice. Cation lattice. And for each one sodium, we have one delocalized electron just kind of floating around in the spaces between. And what happens is each cation is going to have these small electrostatic attractions to every nearby electron. And this is going to be the form of the metallic bond. It is not one individual bond between atoms, but instead this ordered structure of electrostatic attractions between multiple ions. And you can go ahead and make these as big or as many and convoluted as you want, but this is the overall metallic bond. So we have these electrostatic attractions between lattice and our delocalized electrons. So remember, these delocalized electrons are very specifically free to move around, and they do. And as they move around, they continue to kind of break and reform attractions with whatever atoms are next to them, or cations are next to them. So that's kind of how it's different. We have more like a bunch of little electrostatic attractions holding this thing together instead of just like each cation bonded to the one next to it. So that's how it's different from our ionic compound lattices or even our giant covalent lattices. So that's a metallic bond. This is where the first part of the section ends, and we move on to the second, which is general properties of metals or properties of metallic bonds. So we have about 6 of them or 5 of them that we're going to go through. And the first one is simply the luster, which is another way for saying the shininess. And so metals in general are very shiny. And as we're going to notice with all these properties, it's due to delocalized electrons. Specifically, these electrons absorb visible light, the light we can see. And metal is actually very good at like just reflecting visible light mostly. There's cases where we can reflect other ones, but they absorb visible light. Then they vibrate and move, and then they emit visible light back because they need to get rid of the energy that they got and they re-emit it in visible light. They do this differently. So different metals with more or less valence electrons can change. So the electron density of our delocalized electrons changes the shininess. You can see this example where some metals are less shiny or some shine in different colors. So for example, silver, Ag, is very reflective to visible light. But for example, gold, Au, and copper, Cu, these tend to reflect reds and yellows, while they mostly absorb blues. And that's why they kind of have a more coppery or gold color because they're not reflecting everything. They're just reflecting the reds and yellows. So the shininess changes based on that electron density and how they can move within the lattice. So there's a lot of factors that affect it, but that's the basic idea of shininess. It comes from the delocalized electrons absorbing and re-emitting light. Sound. If you're at a desk, what you should try and do, and we call this being sonorous, is go ahead and start tapping on things. You can tap on your screen, which is probably glass. You can tap on your desk, which is probably wood, and then tap on metal. And you'll notice metal tends to have a high-pitched ring. You'll notice things like tuning forks are made of metal. And it's because, once again, we have our delocalized electrons. And that's because these are free to move. And what they do when they move is they propagate sound waves through, whoops, through the lattice. So metals propagate much more differently sound waves because they have so many free moving particles within it. Something you'll generally tend to notice is low density metals are more sonorous. And that's because they have more space in the lattice for electrons to move. More space between cations for electrons to move. So that sound quality comes from, once again, these electrons. All right. Number 3, this is one of the most important industrial uses for metal, and that's malleability. And this is also why I say 5 or 6, because I kind of group these together, malleability and ductility. They're two different properties, but we can kind of talk about them in the same vein. Ductility. Now, malleability is basically like being able, oof, don't know what I'm doing here, being able to flatten or compress the metal. So like if you hit it with a hammer, um, so this is kind of pushing force. Generally, we think about it as flattening metals into sheets, flattening metals into sheets. Meanwhile, ductility is stretching, and that's pulling force, and we stretch it into wires. So we use ductility, the ductility property to make all our metal wires. We use malleability to make our metal sheets, such as like even things like aluminum foil comes from that malleability. All right. So why is metal able to do this? Normally, when you stretch or pull, you break something. Now, with metals, once again, we have our delocalized electrons, but this more deals with the metallic bond. So under stress, layers shift in the lattice. Now, we remember from before with our ionic compounds, when we shift those layers, they then repel and break, and that's what makes them so brittle. However, metallic bonds remain unchanged because it's not atom to atom, remain unchanged. So we can see this when we have, I'm going to go ahead and copy this up here, copy this whole thing, and we'll paste it. So now if we were to imagine that we have some stress shifting the top layer one way and the bottom layer the other way, well, we'll actually just do this again here. If we go ahead and take this top layer and we shift it over, well, I kind of want to move the whole thing now. If we take our whole top layer and shift it over, turns out we still have the exact same attractive forces. We can see right here that nothing changed. The whole layer shift. And what's going to actually happen is what we've got going on here will still be going on right around here. So the whole layer can shift, and yet the metallic bond faces no actual detriment to itself from one way to the next. And so this is why we can stretch it. The bonds will still hold because once again, the bonds are not part of the atom to atom connection, but instead the lattice to its electrons. All right, so that is our malleability and ductility. So now we're going to look at electrical conductivity. Take a moment to realize I have been numbering this and then I didn't anymore. So electrical conductivity, we described this when we talked about properties of ionic compounds. Now, we may remember that the electrical conductivity is the ability for charged particles to move through a space. So take a moment and think about any charged particles within our metals. So if you even think about it for a second, you realize what we're talking about is, well, of course, our delocalized electrons. And so they can move through the space quite well. And this actually means that our metals are very conductive. Another rule of thumb is if we have more valence electrons, we have more conductivity, specifically electrical. And that kind of makes sense because we have more particles to move through that space. And those valence electrons come from the charge. So you might think that calcium is generally better than sodium. and aluminum is generally better than calcium. And so we can kind of think about this in these terms. There's actual charts where you can find the electrical conductivity in the data booklet, I believe. But regardless, it's just a general trend. It doesn't always hold true. There are, of course, many exceptions, as is the way with chemistry. All right, moving on to our last one, thermal conductivity. So thermal conductivity, because I usually cannot spell and write at the same time. Conductivity. All right. So thermal conductivity is, unlike of charged particles, it's the ability to transfer heat. And we generally think of metals as very conductive. This is why we make pots and pans out of metals, because they conduct heat from our stove to our food. Now, once again, of course, this is due to our delocalized electrons, which increase in kinetic energy when the metal is exposed to heat. When they increase in conductivity, they move more throughout our metal, and they end up in areas of low kinetic energy. And so as they move throughout the metal to areas of low kinetic energy, they then collide and transfer that energy. This leads to transfer of kinetic energy and therefore add energy or heat to that area. So generally, we excite the electrons, they start moving through. If we look at our electrons here, if this one's bouncing around like crazy because it's getting hot, it will eventually move over here and bounce around, adding energy to our cations and other electrons in the other area. Now, here's the difference between thermal and electrical conductivity. More electrons does not mean more thermal conductivity. You think it might, but the problem is they get in the way of each other. So when we have more valence electrons or more delocalized electrons, they start colliding with each other, colliding with each other, and therefore they lose oh, that's the wrong lose. They lose too much energy. Or they deposit that energy in other ways. If you get certain metals very hot, they start becoming bright because they're colliding so much that they're releasing energy in terms of light energy, or maybe they're losing it back as heat, radiating it out. So too much electrons means too many collisions happen. They'll slow each other down and they'll just get in each other's way. So these are all the properties of metals. This is how metallic bonds work and hold things together. So hopefully this helps, and have a great day.